Did you figure it out? Not yet. So, cadmium, what did I say? Aluminum cadmium?
Yeah.
Aluminum cadmium? Wait, cadmium on there? There it is. Cadmium plus 2 aluminum all right. What's the voltage associated with the cadmium that you know?
-+4.
And for the aluminum? Okay. So then, if we want this reaction to be positive, which one of these do we want to flip? The aluminum. So if we flip the aluminum, okay, make that positive. Now you can just add these two together, and that will be the resulting voltage that we can get out of this cell. All right? Now, the reaction itself, again, cadmium plus 2. Well, what are we going to have to do before we multiply these together? Can you see? Times this by 3, times that by 2. Okay, you see that? We have to do that. I'm not going to write this out. Oh. 3 cadmiums, 6 electrons I'm going to have to drop off. 2 aluminums, 3 cadmiums, 2 aluminums. All right? Now the voltage associated with this written equation here does not change because I multiplied this by 3 and multiplied this by 2. It's because these E naughts that I have are still for just 1 molar. 1 molar of everything that's in solution. All right, 1 molar of for standard potential, right? The standard E naught, right? So I still get, what did we say, 1.2? 0.26. Okay, very good.
Or
Now,
choosing the other 3 from. I could.
These ones?
Yeah.
We decided that if these two were to add together, this is 2 electrons, this is 3 electrons, right? We're going to need to cancel out. So
we can't change the moles that we get out of this equation based on how many moles of stuff you put.
you can't.
You can, but this isn't doing that.
Well, the standard reduction potential, the 1.26, will be if you have 1 molar of the things in the solution. If you have 3 molar of this and 2 molar of that, it won't be 1.26. It'll be something else.
Okay. So this was just balance the equation.
That's the balance.
And then if we put 1 mole of each in that
Yes.
equation.
1 molar.
That would be that.
Now, like we saw, not all these reactions are going to give us a positive value, right? If we had switched this one and not this one, right, then we would still have a negative value. And we talked about this before. Remember this? Where we said, okay, if I have silver metal and I combine it with copper ions and produce silver ions and form copper metal. Right? Is that going to happen? Is that process going to happen okay? There was a way to tell. How could we tell? The activity series on the back of our periodic table. Do you remember that business? So why don't you turn it over, see if you can tell whether this reaction is going to proceed or not. Who are we asking to be more reactive in this process? The one that I have drawn on this board. we're asking the
Silver.
silver to give up its electrons, right? And, well, it's all about not what it likes to, but how compared to its neighbor, right?
Right, and it doesn't.
All right. So compared to copper, silver is less reactive. So this process will not occur like that. Will it occur the other direction? All right.
It should, I think.
It should. Okay, so here I have some, I guess what this is?
It is silver. Dissolved silver.
Water, silver ion. It's silver nitrate. That's right, silver ion. Silver nitrate. Okay? And then I have a wire of copper. Okay? So, cover your eyes if you're in the first row. All right. So, is it working? Can you see it? Looks like it's getting dusty or moldy. So what's happening? The what?
The silver
The silver is plating out on that copper, right? See it? Did you guys get to see it okay? All right, so now watch. I'll shake the wire. Did you see it all come off? Now there's a bunch of silver floating around in it. So put in some more. I'm also seeing a little tinge to the solution. You see that?
So it's greenish.
Yeah, it's turning. What color do we know copper ions make? Kind of a bluish green, right? Depends on how they burn in the green. If they're in solution, like copper sulfate, give us a blue color, right? All right, so we'll let that go for a while and see if it gets more and more blue. The crumbly stuff in there, the precipitate, that's what? What? Silver. That's right, silver. Silver metal. If we let it go long enough, it'll form a nice little ring for us. The silver? Yeah, we should take it to the pawn shop. This is real silver, I promise. How much do you think they give us? Probably nothing. But it is real silver. Oh, well, in that case, for sure we'll give you $10. Okay. So then, let's see what else we can do. Can you tell me what the E cell is for this reaction? So here's the reaction. We have some redox potentials. There's some standard reduction potentials. There are reductions. All right, which one has to be flipped? Can you tell?
Depending on the top one.
Yeah, the top one has to be flipped because in that reaction up above, nickel is being reduced, or sorry, oxidized to nickel +2, right? So it's going to be 1.77, what, plus or minus?
Plus.
Plus 0.25.
So
That's our standard potential for our cell, our volts, our voltage. That was what we were doing just over here, right?
Oh.
Same thing. Yeah.
well, you give us that little thing like the cathode minus the anode.
Here? This thing?
Yeah, I guess I'm just trying to relate that to the one that's on the product line.
This one right here?
Yeah.
Cathode minus anode?
And how do we decide which
Well, they tell us cathode minus anode, but that's dumb, because that's like a little device that you're supposed to be able to remember for the rest of your life. And that's not feasible, right? But this charge, or this charge, either one of those two tables, are going to always be with you. like the force, right? So if you can figure out how to manipulate these, then you don't have to worry about, is it capital minus capital, right? You just, when you flip them, you change the value, and then you bring them together.
Yeah, because like, that would be kind of confusing. It's like you flip it, that does not change like which side is the.
Yes,
So-
right.
Yeah.
And so they're saying, don't change the sign, just take capital minus in them. That's not improvement on the situation, that's just more tight in mind.
So all we're trying to do is like make it spontaneous and like make it more positive.
If it's a positive value, then that's an indication of spontaneity, which should give you a hint to where we're going. Yeah.
Can you explain again how we know it's positive? So it doesn't depend on it.
Which one to flip?
We don't look at the book.
Well, for this one, for example, we were trying to get a positive value. So we were looking at which voltage would give us a positive value when we flip. For this one up here, we just look at the reaction that they provided. They had to flip one, right? If they're writing a redox reaction, they can't put two reductions in there. All right? They had to flip one. So we identify which one to flip. We change that sign and add them together. Does that make sense? You guys follow that?
Let's use there. So because
Yes.
the iron was on the right side.
Uh-huh. Right.
Maybe it is the half fraction.
Yeah, you have to have that standard potential. Okay. So here's a little representation of our reduction table. So you have this thing being reduced to this. There's the voltage associated with it. And we would like to know if these reactions that we're going to show you are spontaneous. What do you think? Is this one going to be spontaneous? I actually know this one's going to be spontaneous. You know how I know? Because when I was in science class, I had a little teacher do this experiment, and they mixed copper with silver iron. So I could see it happen. So that one I know is spontaneous, right? What's the voltage associated with it?
It's positive.
Positive what? Let's see, the silver's 0.8 plus the 0.34, right? Oh, no, minus the 0.24, sorry.
Because it will-
Yeah, they flipped it, right? Yeah, duh. Very good. We'll do it again. What's the voltage for this reaction? Copper's the 0.34, and the lead ion is the, needs to be flipped, right? So it's 0.13. So 0.47, is that what I heard you guys say? All right, very good. Any questions about that? One more, or is it too easy now? Yeah.
Alright, so am I thinking the right thing when I think that we're just always looking for a positive number?
Well, you know, they could have different kinds of questions. So here they're asking, what is the reaction spontaneous? And if it's a positive value,
Then it is.
then it is spontaneous. But I'll bet, because it looks like there's no more room on the slide, I'll bet this one is not spontaneous. All right? We want to give us a little bit of both. They had to choose two. You can't be free even for everybody. Room for 3 examples. One has to be twice. It's not. We don't like spontaneous. No favoritism here. But you can tell that it's not going to be favorable because the resulting voltage is what? Okay. All right? Everybody figure out we got those values? Excellent. And sure enough, looky there. Delta G, which is what?
Energy.
Yeah, it's free energy relates to what? Why did we invent delta G?
I can't remember.
It's work and it's also
Heat.
heat, all wrapped up into one thing that tells us spontaneity, right? Gibbs free energy is what the delta G stands for, and it's all about spontaneity, right? And so we can relate spontaneity to delta E. We have to throw in a negative sign there. See that? Right? And I'm less interested in you guys using this equation, more interested in being able to see what it means, sort of thing. What does the N mean here? Number of moles of what? What do you think? Number of moles of electrons that transfer from one side to the other. So, in this reaction, how many moles of electrons transfer? 6. 6. Can you see 6? And multiply it by 2. That's 3. 3 times 2, right? So,
One electron is 1 mole.
yes. So N would be 6 in this case. All right? So, F is a constant that allows us to relate, and it's 96,500 coulombs per mole of electrons. E is volts per coulomb, all right? So F allows us to get into joules per mole. E is joules per coulomb, is that what I said? Did I say that? E is joules per coulomb. Faraday's coulombs per mole of electron, and moles of electron. We end up with joules for delta G. So the big take-home message is that we can identify the delta G value, spontaneity, with our E. Okay? You know they're going to give you this equation. So we don't need to actually solve for the delta G with the equation, but could you tell me how many moles of electrons transfer in this process? What the N value would be?
1.
Negative
-1.
What?
-1.
Well, silver did what? Gained or lost how many electrons? Gained 1. Copper lost 2. So who's it going to be? Is it the 1 or the 2? Has to be the 2, right? Because silver's not going to, or copper's not going to be able to do anything unless silver ponies up and gives it 2 electrons, right? Or gets 2 electrons. Does that make sense? When we balance this, we're looking for N in this equation. So we can get E, right? We can find out what the reactions are, add them together. F is a constant. N is the number of electrons transferred to the balance of reaction. So we're looking for N.
So it's not like, so in my head I was adding them both up. So it's not.
Well, it's not 3 electrons. It's because, well, let's look at this real quick. What's the oxidative half reaction here? What's the oxidative half reaction? Copper metal going to copper plus 2 and releasing 2 electrons, right? The reductive half reaction, silver ions getting an electron to form silver metal, right? Now, if I want to add these together and get the overall reaction, I'm going to have to multiply this one by 2 to have the balance. All right, so the process is this giving up 2 electrons to 2 silver ions, taking those electrons, forming 2 silver atoms, and resulting in plus 2 copper. So that's N value of 2 electrons. All right, so we would take the delta E. Did we find it on that previous slide there? E naught? What was it? 0.46? There it is. Multiplied by 96,500 and times 2 for our moles of electrons. And just like the 0.46 was positive, the delta G ends up being a negative value, right? Is delta G going to be positive or negative for this one? Negative. This is the one we just did, right? It had a positive voltage. How many moles of electrons? What's the N value going to be? 2? Is everybody okay with that?
So we just take too on the last one, because it was, well, after we completed the balance, they were just saying that it was like the bigger electronic transfer, I don't know.
Well, you kind of have to just have them combined like this and see what's necessary. Because like the last one, I think it's a 3 or 2, right? So that'd be again 6 electrons. That makes sense? So this one here, we can see that 2 electrons transferred. And this one, how many electrons transferred for this one? This was 6, right? Chromium gained 3. Manganese lost 2. And so that ends up needing to have, in a balanced equation, 6 moles of electrons. E naught was a negative value. Delta G is a positive value. Okay. Just like we can get the delta G, we can also get the K. Remember that old equation, or the equation from last class, the last chapter? K equals E, what was up there before? Negative delta G. Negative delta G. Now it's positive NFE over RT. And before it was negative delta G over RT. Okay, so it's the same thing. The delta G is replaced with what it equals to, which is NFE. So we are not going to do these. This equation here, called the Nernst equation. Yeah, the Nernst. It allows us to relate E naught to different concentrations other than 1 mole. So here's our equation to do that. Does this look like some other equation that we introduced not too long ago? The lifeguard equation, Henderson-Hasselbalch. Remember that one? What was this? pH equals pKa plus the log of this relationship, this ratio, right? So it's very similar. We have some extra baggage because we're dealing with the number of electrons and some constants that need to adjust it a little bit. But similar type of thing. Try and find E under non-standard conditions, and we relate it to our function. Yeah?
Do you use this?
No.
I mean, like, in your
And I make fuel cells, right?
What's it for?
Oh, it's for using. If you have to, you go to use it. But my fuel cells are maybe I can use it, maybe I should. But my fuel cells, there's a lot of stuff going on, and you can't tell what the concentrations of the different ones are. You put some in there, but there's other things that begin to happen when you put a lot of stuff into small space. Just because you dissolve stuff in there doesn't mean that you actually have the known amount of stuff in there. So, yeah, well, we call it activity. Just because it's there doesn't mean it's actually active, doing what you would expect it to do, because it can get complex in other ions. So I haven't found a lot of use for identifying actual potential. Usually if I want to know what the actual potential is, I just plug it in. We'll now, is that potential I should expect? There's too many variables for me to really be able to hammer this out. Yes. I don't. Maybe I should. I don't think so. Get along okay. All right, so the Nernst equation allows us to relate what? E naught to E under whatever conditions we have. Okay. Here is something we want to do. We want to have a discussion about current, all right? So, hopefully now, you can answer your kids' questions, at least to a rough degree, about what voltage is, right? depends on the two chemical reactions that are occurring, their standard reduction potentials, right? But current is different. Current is just the flow of electrons, the number of electrons in coulombs per second. So amps are measured with units of coulombs per second. Coulombs per second. Okay? So, whenever you're dealing with amps, we're talking about how many coulombs of electron charge is flowing per second. And you can answer questions like this. What current must be supplied to deposit 3 grams of gold from a solution of gold chloride in 200 seconds? Okay? Current. What current? What is current? What are our units for current, did we say?
Coulombs per second.
Very good. Coulombs per second. I can start with 3 grams of gold. Okay? Coulombs is, well, Faraday's constant tells us that there's 96,500 coulombs for every mole of electrons. Okay? So that'll help us. If we can identify how many moles of electrons we need, we can identify how many coulombs of charge we would need. So if I go from grams of gold to, where do you think we're going to go? Moles of gold. Because there, we can then relate moles of gold to moles of electrons. Right? And then moles of electrons can be related to 96,500 coulombs. Right? So I'm in coulombs, and now I just need to get it in 200 seconds. Is that all? Okay. Put it in your calculator, find an answer, and then try to tackle the second one. Really, nothing new here, right? This is all business as normal, except for we have one more conversion factor, which is how many coulombs are in a mole of electrons.